So let's continue with the exercise as we mentioned it. I hope that it was possible for you to review uh, the course in the presented part. So we reached the exercise 4 here to deploy a cellular network. And we want to deploy a cellular network which is in a big city, which is DSM cellular system. We have 500,000 citizens. And we are using frequencies with a reuse factor of 9. So we have a reuse factor of 9, and the operator will use 63 frequencies. Okay, so this operator is able to use 63 frequencies. Reuse factors cluster size equal 9. Okay, and the data related to the traffic. So the environment of this operator, they detected 3 different zones, zone A, zone B, and zone C. A and B, they have 20% of the citizens and 60% are in zone C. So we have here 20%, 20%, and here 60%. And the required quality of service in terms of blocking rate. So maybe in zone A, we accept 2% as a blocking rate, but it should be 1% in zone B and 1% in zone C. So in each cell, so it's already adopted by the operator that we should reserve in each cell one BCCH for the broadcast, one IT for the BCCH channel, and 2 for the SDCCH channel. So in this case, in each cell, we have 3 ITs that are reserved for the signaling. Okay. So the first question here, what's the offered traffic in each zone? Okay, so what's the traffic uh, offered in each zone? Okay, so let's calculate this traffic. I hope that it was possible for you to check or to do this exercise as I mentioned in the last presentation, in the last session. So here we know that we have the traffic per subscriber at the busy period is around 30 million long. So for us, we know that that the number of users in each zone. So it's just a simple calculation. We can do it. So we have in each zone the number of users. So let's start by zone A. So in zone A, the number of subscriber. So zone A, number of subscriber, it's equal 20% of the all subscriber, which is 0.2 times 500. In this case, it will be equal around 0.2. It's 100,000 subscriber. And traffic in zone A, traffic in zone A, it's equal AA, let's say, and it's equal 100,000 times 30 millierlang. It will be equal to 3,000 erlang. We calculate for zone B, because it's 20%, it will be also A, B equal 3,000 erlang. And for C, zone C, it's equal AC because it's 60%, so it's 3 times. It will be after calculating it. And then you can do the calculation, okay? So now I know the traffic offered in each zone. Okay, so this is the answer of A. For B, what's the maximum traffic supported by a cell in each zone? Okay, let's start with zone A. In zone A, what's the difference between zone A and zone B and zone C? It's the quality of service. Okay, so B and C will be similar, but A will be different. Okay, so we have 60 frequencies over 9, so we have 7 frequency per cell. 7 frequency per cell will give 56 IT. Minus 3 for the signaling, we have 53 IT per cell. Okay, 53 IT in zone A. In zone A, 53 IT, which is the 53 physical channel, with a blocking probability. This is TCH with a blocking probability 2 to power minus 2. In this case, we are able to support 43.06 Erlang per cell. We can find this number from the table. Okay, and if you want to see for zone B and C, for zone B and C, zone B, and similar for zone C, we have 53 ITTCH, and the probability it is 10 to power minus 2 based on the table, because the probability the blocking probability is less, which this means that we have a higher quality of service in comparison to A. The quality of service is better in quality, so that's why the traffic will be less in the cells of zone B. Okay, in each cell of zone B. Okay, here it will be 40, and we can find this number of the table. And also for zone C, it will be 40.6 Erlang per second. Okay, so what's the total number of cells to be deployed in the city? So because I know the traffic by zone, and I know the traffic that I can support by a cell in each zone, so I can find the number of cells of its in each zone. So in this case, number of cells in zone A is equal NA. It's equal 3,000 Erlang. The traffic per cell that we can support is 43.06. In this case, we have around 70 cells. And for number of cell in B, it's equal NB, and here it's 3,000 over 40.6. It's equal to 74 cells. And number of cells in zone C, which is NC, it's equal 9 over 40.6. It's equal 222 cells. And remember that in zone A and in zone B, we have the same traffic, but because the quality of service we need in B is higher than the quality of service in A, that's why we need more cells, okay? So this is the total number. The total number, in this case, it's equal to 70 plus 74 plus 222. It's equal to, okay? So this is the total number of cell. What's the total number of site? So in this case, the total number of site, if we are using one cell per site, if we are using, let's say, 3 sectorial, we should divide them by 3. And if we are using one cell per site, we will have the same number of site. But typically, when we are doing site in cellular system, we use a 3 sectorial site. With a 3 sectorial site, it's possible to have, in this case, divide by 3, it will be around 122 sites. If we have monosite, this means that we have one cell per site. In this case, we have 366 sites, okay? And the last question is, what's the total number of cells to support the traffic in the city if a growth factor of 20% and a margin safety of 5% to be taken into account? So you should repeat, maybe you can do it by yourself. In this case, instead of using A here, A, B, A, C, we should multiply them by 1 plus 0.2 and 1 plus 0.05. And you can recalculate the traffic and the number of cell and so on. So this will be the same, but the traffic will increase, and for sure the number of cells will increase. So maybe you can complete it by yourself. It's okay. It could be an exercise for you. So the part E, you can do it by yourself. It's not very complicated. Okay. Let's move to the exercise 5. Here we are doing a link budget. Consider the GSM system where we have BTS and the mobile station. We have the following characteristic. The transmission, the BTS is 39 dB, 3 dB loss, gain of the antenna 14 dB, sensitivity, so the reception is minus 1.0.4, and the diversity is at the reception. Okay, the diversity is at the reception. Okay, so and for the mobile station, the terminal, we have the transmitted power 33 dBm and the sensitivity minus 103 dBm. Using the link budget calculation show if the characteristic will lead to have a balanced link. So we should have the study at the uplink and the downlink. Let's go at the uplink. So in the uplink we have the received power, which is the sensitivity here, the PR BTS, it should be equal to the sensitivity dBm. It equal transmitted power, which is 33 dBm. It's at the uplink, so we have the gain of the diversity plus 5 dB. Then we have the path loss. Sorry. Let's put them in the right order. So we have the mobile and we have the BTS. So here is the transmitted power. So we have the path loss. So minus the path loss uplink, plus diversity gain at the receiver, which is plus 5 dB. And we have also the gain of the antenna, which is plus 14. And we have the loss in the feeder, which is minus 3. And in this case, we obtain that the L path loss uplink will equal 104. We can give them to here plus 33 and minus 14 minus 5. So in this case, it will be equal to 143 dB. For the downlink is the received power, which is the sensitivity at the PR mobile station equal minus 913 dBm. The transmitted power at the base station is 39 dBm minus the transmitted at we have the loss in the feeder, which is minus 3 dB. We have the gain of the antenna, which is 14 dB. And in this case, we don't have gain of the antenna at they are not mentioning the gain of the antenna. Okay, so that's why we have only the path loss and the downlink, which is LP downlink. And in this case, LP downlink equal, let's see, 39 minus 3 plus 14, which is equal to, okay, minus, okay, which is equal to 15 in the other, okay, it will be minus 15, so it's also equal to 153 dB. So in this case, we can conclude that the link budget is, the link is balanced, okay? So because the link is balanced, we don't need to make any configuration of the parameter. So here in part B, we say what's the radius of the cell considering a path loss is equal L equal 136 plus 35.2 log R log base 10 R, where R is the radius. This is a simple formula of the path loss as a function of the radius of the cell. We assume that we have, let's say, a circular cell. It's an assumption. So in this case, if we have 153 153 dB. In this case, we can calculate it as follows. So we have L equal 153. Okay. So in this case, L equal 153, which is equal to dB, which is equal to 137 plus 35.2 log 10 of R. R is given in kilometer. So in this case, we have R is equal, I have to make the calculation. So 153 minus 137, okay, is equal to 16. Okay, so R 16. So R equal 10 to power because it's log 10. So it's 10 to power, okay, 16 over 35. It's okay. So in this case, we can find it, it's equal to 2 power 84 kilometer. Okay, I want just to verify. 35 here, 0.2. 16 over 35.2. Okay, and I want to calculate 10 to power this number. Okay, so 10 to power. It's okay, it's fine. So here we calculated the radius of the cell giving this path loss. Okay, and as I explained before, if it's not balanced, you will find that the cell, as I said before, if in one of them it's not balanced with the uh, with the uh, with the budget where the path loss uh, uh, is smaller. So in this case, the radius of the cell will be less, and that's why in this case one of the communication will not work properly. Okay, I hope it's clear for you. And let's move to the last question. And in this question, remember that when we presented the frequency allocation, we said that in this case, we should avoid that in a cluster, we should not choose the same frequency on the same cell. Okay. This means that the frequency is used only once on a cluster. And also to avoid the adjacent interference, it's well known that we can make a kind of, let's say, to avoid that adjacent frequency. This is done here. So here, when have enter cell, it was in the previous chapter, so we can just apply it here. The idea here is that we want to calculate the consider the following GSM system. We have three sites, and each site is with three sectors with three cells. And we have the required frequency in each cell. This means that Y1 we need 4 frequencies. In Y1 we need 4 frequencies. In Y2 we need 3 frequencies. In X1 we need 4 frequencies, and so on. Okay. So in each cell the number is the required frequency. So the total number here is 3 plus 4 plus 4 plus 3 plus 3 plus 3 plus 3 plus 4. It's 30 frequencies. So in this cluster we have 30 frequency, okay, and we want to use them on this cluster. So this means that the frequency is used only once. And what's the reuse matrix? It's a well-known term in radio network planning. Okay, in this case, if we want to define the reuse matrix, so it's the matrix to see the separation between the frequencies within each cell and within the cell and the neighboring cell. So in this case, in order to find this reuse matrix, so we have to put the different x1, x2, x3, y1, y2, y3, z1, z2, z3. And here x1, x2, x3, y1, y2, y3, z1, z2, z3. And typically, in order to avoid the interference, so they say that if we want to use the frequencies in the same cell, so we should have at least three hops between the frequencies. So if I'm using F1, I should not use F2 and F3. I should move to F4 within the same cell. So this means that we have, let's say, a gap or a guard of three frequencies. This is F1, F2, F3, F4. That's why we consider it as 4, sorry, as 3. Between two adjacent cell, here we have two cases. If the adjacent cell are on the same side or they are on the different side. If they are on the same side, like for example, x1 and x2, they are 3 sectorial but on the same side. Here, the preferred, let's say, gap is 2. And if for x3 it's also 2. But the other adjacent that they are not on the same side, they could be 1. This is at least. When we say 3, it means that at least we should respect the 3. If it is 4 or 5 or 6, it's okay, no problem. But the reuse matrix will give us the minimum number, okay, of gap or of frequency to be avoided. Okay, this is the minimum. Okay, and if it's better, if it's more than this number, it will be okay. So similar for x2 with x1, it will be equal to also 2, but x2 and x2 it will be 3, and x2 and x3 it will be also 2, and it will be 1 with the others. And x3 it will be 2, 2, 3, and 1 with the other. So that's why we can complete. The diagonal will be always 3. y1, y2 here they will be 2, 2, 2, 2, and the other will be 1. Okay. So after doing that, this is based on this matrix, we can allocate the frequencies. Okay. Based on this matrix, we can allocate the frequencies. So that's why in part 3, now that we have 30 frequencies on this system, we want to propose an assignment, a frequency assignment plan. Okay, this means that which frequency will be allocated to which frequency will be allocated to which cell. Okay, so I will start this with you, and I will let you complete it by yourself. So I will add. Okay. So I will just put here the reuse matrix, which will be x1, x2, x3, y1, y2, y3, and here x1, x2, x3, y1. It was 3, 3, 3, 2, 2, 2, 2, and 1 for the all others. Okay. So for the reuse, for the assignment plan, here we can do it in different way, but the essential is to respect the reuse matrix. Okay, so in the part C, we have x1, x2, x3, y1, y2, y3, z1, z2, z3, and we have the number of frequency f1, f2, f3, f4, f5, f6, f7, f8, f9, f10 until f30, because we have 30 frequency. So which frequency will be allocated to x1? Remember that to x1 we need 4 frequencies, okay? And those frequencies should allocate it such that the difference with S2 with the same frequency as X1 in X1 is 3, with X2 is 2, and with all other it will be 1. Okay, so this means that we will not use the same frequency in the other because it's a cluster. So here typically I will use 1, and I will use F1, F4, and F7, and let's say F10. It's okay. So I respected that. So now for x2, I should allocate 3, okay? And when allocating 3, I should also respect that within x2, the difference should be 3, and with x1 and x3, the difference should be 2. And with all other, the difference will be 1. So if I put F2, for example, it will not be accepted because the difference between X2 and X1 here, it's not 2 and it's not respected, okay? Because here the difference is 1 and it should be 2 because they are on the same side. So that's why I cannot use it here, and I have to move to start by, for example, here F10, F11, F12, for example, here F9, 11, 12. So I start by 12 here, and here the difference is 2, and after that F12, I should move 3, 12, 13, 14, 15, and then until F, for example, 15, 16, 17, 18, here. Okay, so here the difference is 3, the difference is 3. Okay. And for y, it should be also from this side. And after that, I should add y2, y3. The essential is that, okay, any frequency should be used only once. So here, the total here will be 1, 1, 1, 1, only one. Okay, the frequency should be only used once. Okay, and here the total, if I want to add those 1, they should be 4, 3. Okay, and here 3, the requested number. And we should respect that within the same cell, the gap between the frequency is at least 3, okay? And between the two frequency, the two cells on the same side, at least 2, and it's at least 1 between the other frequencies. So I will let you complete this table, okay? And maybe you can arrive at certain time and you cannot continue. Okay, so maybe in this case you can restart, and instead of using 3 here, you can say I will start by, for example, I will start by using F1 and F5, for example. It's possible to use F1, F5, and let's say F9. Okay, in this case, after that, you can use here F3, for example. Okay, so maybe you can start in another way, but the essential is that the minimum number of separation between the two frequencies within the same cell will be 3. Okay, so I will ask you to complete this. This is very important, and this will give us uh, allocation plan. Okay, how to allocate the frequencies for the cells in order to respect the different part related to the interference within the cell and to the adjacent interference coming from the other cells of the adjacent frequencies. Okay, so this is a simple example. We do it manually just to understand the concept. But if we have a big number of cells and we want to use advanced algorithm, we have some, let's say, genetic algorithm or some advanced algorithm in order to run them and to distribute the frequencies. And this distribution is done for a fixed allocation. It's also possible to have allocation with borrow. So this means that we have dynamic allocation and we can update them according to the request traffic in different cell for a certain period. Okay, so this is just to give you an idea. I hope that it was clear for you. And if you have any question, please you can send me and we can discuss during next sessions. Okay, so this will end chapter 3 regarding GSM. And we will start next chapter by presenting UMTS. And after that, we will move to the fourth generation. Okay. So I hope it was very clear for you.